of 1 over square root 4 minus x squared dx converges or diverges. I had just showed it to you in the beginning of the class. Why is this improper? This is improper because at one of the limits, the function is undefined. When x equal to 2, the denominator becomes 0, the function is undefined. So this is an improper function. We need to take a limit. Say limit b approaches 2. Is that right? So we have a discontinuity at x equal to 2. We will write integral 0 to 2 1 over square root 4 minus x squared dx will be, how do you write this as a limit now? Will be limit b approaches 2 of integral 0 to b of that quantity. Alright, now, how do we integrate this? This is actually a standard integral you should be able to pick out quickly. This is of the form integral 1 over square root a squared minus u squared du, which is, alright, quickly, what's integral 1 over square root a squared minus u squared du? Is arc sine u over a, where u is x and a equal to 2, a squared minus u squared. Alright, so this integral is the arc sine form with a equal to 2 and u equal to x. 1 over square root a squared minus u squared du is arc sine u over a. Therefore, this will be limit b approaches 2 arc sine u over a, means x over 2, and the limits 0 to 2. Let's apply the upper limit and then the lower limit. That will be when b goes to, when b goes to 2, 0 to 2, arc sine of, when x equal to 2, it becomes arc sine 2 over 2, that is arc sine 1, minus, when x equal to 0, it is arc sine 0. Alright, what's the value of arc sine 1? Sine of what number is 1? Sine of pi by 2 is 1. And what is arc sine 0? Sine of 0 is 0. Therefore, arc sine 0 is 0. Therefore, this is pi by 2, this is 0. That means the value of this improper integral is pi by 2. The improper integral converges to pi by 2. Alright? Let's do another one. A 5 metric ton rocket is fired from the surface of the Earth to outer space. What is the work done to overcome the Earth's gravitational force? Now, how far has the rocket traveled when half the total work has occurred? Now, you must understand that this is something that we have done earlier on in Unit 1 about work done when the force does not remain a constant. As the rocket lifts off from the Earth, the force changes. And we said the force changes according to what equation? F equal to k over r squared, where r is the distance of the rocket from the center of the Earth. So, if you have the Earth in here, that's your Earth, that's the center of the Earth. This distance is what we call the radius of the Earth. And the rocket is going to be lifted off from there. And at any time when the rocket is here, that distance is actually r, the distance of the rocket from the center of the Earth. So the force at any time will be k over r squared. Is that right? Now that's what actually that means. Let's write these things down now. Okay. Now, the weight of the rocket on the surface of the Earth. Now, remember, the force that needs to be applied to lift the rocket is its weight. So, what is the weight of the rocket on the surface of the Earth? The weight of the rocket on the surface of the Earth is its mass times the value of g on the surface of the Earth. And the mass is 5 metric tons. So its weight will be its mass times the value of g on the surface of the Earth. We can use it as 9.8 meter per second squared. So the weight of the rocket on the surface of the Earth is 5,000 kilogram times 9.8 meter per second squared. That is 49,000 Newton. And this weight will change as the distance increases according to the equation I just gave you. Weight will change as k over r squared. So using Newton's law, the weight of the rocket on the surface of the Earth can be written as F equal to k over r e squared. You see, if F equal to k over r squared, where r is any distance, but when the rocket is on the surface of the Earth, that distance is the radius of the Earth. And you know the value of the radius of the Earth. Now, we know the weight of the rocket on the surface of the Earth here. We know the radius of the Earth. Therefore, we can calculate that k. That is the first thing to do in this problem. And the radius of the Earth, you know, is 6.64 times 10 to the power of 6 meter. And using F equal to 49,000 Newton and RE equal to this value, we can find the value of K. The advantage there is K doesn't change with altitude. What changes is the weight. F changes with the altitude. But K remains the same. Wherever you go, that K is the same. So once you find the value of K, we can use it anywhere as the rocket goes into space. So let's find the value of K by placing F equal to 49,000 and R equal to this value. And that gives you K equal to this big number, 49,000 times 6.64 times 10 to the 6, all raised to the power of 2. And that is 2.16 times 10 to the power of 18. That is the value of K. Well, it has also a unit. In mathematics, we really don't consider much of that. Its unit will be Newton meter square. Newton meter square. All right. Now, the work done to overcome the Earth's gravitational pull is given by, remember, what we're doing is we are taking this rocket from the surface of the Earth and away from it to infinity. So, the work done will be integral. The distance at the surface of the Earth is RE. And the distance when it goes to infinity will be infinite. So integral RE to infinity K over R squared dr. Isn't it? The work done is the force multiplied by displacement. And because this force does not remain a constant throughout the displacement, we assume that this force remains a constant during the very small displacement dr. So we calculate that dw, the work done for that small displacement, and then integrate it from the surface of the Earth all the way to infinity. The value of r on the surface of the Earth is the radius of the Earth. That's the meaning of this integral. And we know the value of k, so we will now write this as a limit. This is the integral. This is an improper integral because that limit is infinity. So that integral now is w equal to limit b approaches infinity, integral RE to be K over R squared dr. What is the integral of K over R squared dr? It is negative K over R, and the lower limit is RE, the upper limit is B, and if you apply that, apply the upper limit, it will be negative K over B, that's the upper limit, minus negative K over RE. That's right. Yes, and now tell me, what is the value of K over B when B goes to infinity? In the limit when B goes to infinity, K over B is 0. Any number divided by infinity is 0. So this will be 0, minus become positive. So this will be K over R, 0 plus K over R. And K we know, R we know, and that gives you the total work done to take this rocket from the surface of the Earth and put it away from the Earth. That means the rocket will never come back. It has gone completely out from the gravitational field. The total work done is 3.25 times 10 to the 11 joules. That means this is an improper integral that converges to this. Now we have a second part for this problem. You remember what that is? Second part is, when half this work is done, what is the altitude of the rocket? What is the distance of the rocket from the surface of the Earth? That is the second problem. So, when half this work is done, half of this work is 1.63 times 10 to the power of 11, isn't it? Half of this, just divide this by 2. So half of this will be 1.63 times 10 to the 11 joules. When this is the work done, how far is the rocket from the surface of the Earth? What all we need to do is put W equal to this value and then evaluate that integral one more time. Is that right? And find the value of that R. That's what we need to do. So we want to find the value of R when the work done equal to this. And you know, work done equal to integral RE to infinity K over R squared dr. And that will be, here we are not going up to infinity. We are only going up to R, up to the altitude which we need to find. So we will replace that infinity by R, where K, we know this value of W. So W equal to integral RE, the radius of the Earth, to R, the altitude that you want to find, K over R squared dr. And the integral K over R squared dr will be negative K over R from lower limit, the radius of the Earth, to upper limit R that we need to determine. And that will be, replace the upper limit, that will be negative K over R, R is replaced by R, minus negative K over RE. There you go. And you have now the two negatives make it positive. So you have 1.63 times 10 to the 11 equal to negative K over R plus K over RE. Now, do we know the value of K? Yes, we calculated the value of K earlier on. K is 2.16 times 10 to the 18. And the radius of the Earth, RE, is 6.64 times 10 to the 6 meter. And you know the work done. So, we know this value, we know K, we know RE. The only unknown is the lowercase r. So, that will be, you can say